Yeah, welcome guys. I'm Sebastian Herold. Let me just shortly introduce myself before I start with data warehousing and streaming. I'm working as principal data engineer or slash architect, whatever you call it. So I'm not the architect working in the ivory tower. I'm working next to the team to try to improve the people that I'm working with. So I started working with Immobilien Scout, built a data platform there. Maybe you heard of the Data DevOps Manifesto I talked about 2 years ago. And yeah, now I'm since 2 years with Zalando, and I first started to work on the ML productivity thing, but now switched to streaming data warehousing. Probably you heard of Zalando. Zalando is quite a big company. We are almost in every market in Europe, having more than 28 million active customers, more than 14,000 employees, and yeah, more than 400K product choices for t-shirts, shoes, and whatever you like. But on the other side, we also have tech at scale, right? So we started having an AWS account for every team, which is maybe not a good idea. So we ended up with more than 350 AWS accounts. We have more than 250 development teams. More than 100 Kubernetes clusters. There are good talks about this as well. And yeah, so we don't only have one data lake, we have many data lakes, right? So we have different business units. They have really completely different data. We have logistics, we have media solutions, which do all the advertisements. So we have more than one data lake, which is more kind of a data mesh architecture, if you want to say. And yeah, since many years, we are also having this microservice architecture. So we ended up with more than 800. I didn't find out the right number. I guess it's more than 1,000, but I just want to make sure that I don't tell something wrong. So it's definitely more than 800. Let's say it this way. Okay. Let's start with the why. So Zalando had a classical central data warehouse for many years, so worked really well. So the company was small, but it grow. And yeah, so we wanted to answer the question why our central data warehousing does not succeed anymore. What is the problem in the last 2 or 3 years that somehow make the data warehousing so painful for the company? So first of all, you have seen we have so many microservices. And microservices and data warehousing does not fit together really well. So you have a lot of unstructured data, so a lot of JSON objects flying around Kafka or data lakes or whatever. And so to push these unstructured data into a relational table is tricky and does not work really well usually. So you need convert them, and yeah, so you have maybe one event with nested structures. So in the relational data warehouse, this updates 10 tables because it's a nested structure, and in the data warehouse, this is covered by 10 tables, which usually are joined if you want to do some analysis on it. So this is tricky. Second thing is, having everything in a central data warehouse does not fulfill the need anymore that data sets are needed distributed. So we have many data lakes. We even have many data warehouses. So people started using Redshift or MS SQL. So in bigger companies, the question is more which technology you don't have, right, than which technology you have. So we have an umbrella of storage technologies. So, and the data is needed there. And if you have everything in a, let's say Oracle data warehouse, you don't get this data out easily through a JDBC connection. Yeah. So if you want to suck 1 terabyte of data through a JDBC connection, this will take some time. And what we noticed over the last years is that more low latency is required. Why? We have AI use cases where data need to be enriched, or for example, fraud protection. You don't want to have the fraud detected maybe 1 week or 1 day later. You want to have it immediately, because so if you order something, the order will be processed in the logistics center hours after you ordered it. So we only have this little time frame to detect whether this is fraud or not, or whether we sent this 500 euro jacket to a new customer that somehow used the address of another customer. And so you really need low latency for all this data. Then we also have other data warehouses. So what we had before is we had a central data warehouse. It's okay, the data is ready at 8 o'clock. So people come to work and can analyze the data. But now we have many data warehouses. So people need the data from the central data marts in their data marts and do some further processing. So it's not enough to have the data ready at 8. You need to have it at 3 or 4 or whatever. And we have more near real-time use cases. So Cyber Week is coming up, which is Black Friday and everything, which is a huge thing for Zalando. So, and all the campaign management we do around it. So we don't want to know whether the campaign is successful or whether the Black Friday works on the next day. We want to know it during the day how it works, and whether we need to scale, or maybe even. So last week we had the problem that we packaged so many packages that DHL or Hermes couldn't even take all these packages. So we had to lower our marketing effort to not overload DHL. So this kind of thing is you want to know during the day and not the next day. Oh, sorry, that's my bad. When it comes to low latency event integration, we see that for other purposes, people do the same event integration as we do in the data warehouse. So we are not the only ones doing it. So to avoid having the code and the integration code duplicated, because event integration is tricky. You need to know the domain. You really need to have data quality right. So you better do it in one place than in many places to avoid errors and to ensure data quality. So if we can provide the data in low latency, we can, on the other hand, provide data to backend services that did the event integration before on their own by just taking the data warehousing data because it's ready so fast. So yeah, taking all these disadvantages was clear for us. We need something faster. We need streaming. Yeah. And yeah, let's take one example. Let's take a sales order, right? So we have different events. We have many. This is even a simplified version, right? I guess we need 10 or 15 events to really have the whole sales order picture. But let's say we have one event which is called order created, where you get the information that there's an order ID, order items, and on the order date. So someone ordered something. And after this, so usually the payment information comes in. Yeah, so he had paid wire, I don't know, PayPal, credit card, or whatever. And yeah, then a few hours later, we received a shipment created event. So they prepared a shipment for a specific order. They say which items are shipped. Maybe there are multiple shipments for one order. This could happen if the goods are distributed over multiple physical data warehouses. And not data warehouses, warehouses. And actually, yeah, someone later, an item is returned. Yeah, so you know, in the fashion industry, the return rate of goods is really high. So it's no secret that Zalando has a return rate of about 50%, right? So 50% of the clothes are sent back to us. It really differs from category to category. So I think female dresses have a return rate of about 80%. Not sure why. while underwear usually don't have such a high return rate. Okay, and all this, so during the event integration, what we want to do is puzzle all these pieces together into one sales order. But the events come in one after another, so we start with an incomplete picture here, right? So maybe we get the order created first, so we can only fill in the order ID, order date, and the items, and later on we can say, okay, it has been shipped or returned or paid, whatever. And at the same time, we have calculated fields, which, I don't know, the sum of an order or the GMV that we do, so how much money do we earn with this order. So there are calculated derived fields from this input, usually in data warehousing, which is important for the reporting. Okay, so how we started. So in Zalando, we have a central message bus. It's Kafka-based. It's called Nakadi. It's open sourced, and it's a framework around Kafka to make it a little bit more nicer to work with. And all the topics for all these events that I showed you in the previous slide are dumped to S3. So there's a latency of about 3 or 5 minutes, depending on the scale and the throughput. So we received this data quite fast. So what we did is, okay, so we wanted to do a Spark streaming. Let's take a Spark streaming job. There's this nice Databricks S3 SQS connector. So all these files create an event in an SQS queue. The Spark streaming job reads this SQS queue and only reads the new files from S3. This is really nice. But yeah, where do we put the results to, right? And we had a lot of delta lakes and so on. So the first approach was, okay, we use a delta table, right? So it's really nice. You can update. You heard a lot of asset transactions and all this. So let's put everything in a delta table. And it worked really well. Because we started from scratch, the data size is small, everything is good. And this delta table could also be used from other Spark jobs downstream. This is this delta lake architecture that you heard a lot about at this conference. But wait, there was something important. We need to integrate historic data. So we have the data warehouse full of the last 10 years of orders. And if you receive now a shipment event or a return item event for an old order, we don't have it because we somehow needed to decide, okay, we start reading all the events from, I don't know, 1st of September. So if there is a item returned from an order of August, we didn't have it in the delta table. So what we needed is we need to read all the data from these central data warehouse and put it into the table as well, which is okay. So we had some kind of a bootstrap job, but the delta table is not megabytes anymore, it's gigabytes, right? So this, yeah, you could do, but it blow up our infrastructure somehow, right? So we had about 500 million orders in this delta table. So the table was about, I don't know, 150 gigabyte. And so we did micro batching in the Spark streaming job. And the batch time for each micro batch increased to 2 hours. Why? Because if you use the merge command, on large tables and only want to update the needle in the haystack for each batch, we only updated, I don't know, 0.1% or 0.2% of the table of the data, then this is tricky. So because you can either decide to have the delta table in big chunks of, I don't know, 250 megabytes, but if you want to update one single row in this 250 megabytes, Spark need to read the whole file, update this one row, and write 250 megabytes back. Or you can optimize for, okay, I don't want to read so much and write so much, so I have smaller files, but then you end up with many small files, and this is also slow. So this is kind of a contradiction, and I think in even one of the talks yesterday, Databricks recommends, so if you have this needle in the haystack problem, don't use delta tables as a state store. So I'm not saying that this is true for every of your use cases. For us, it was tricky. So take the merge command with care is the learning here. So, okay, we needed to come up with something different. And what we did is we introduced snapshot and changes tables separated. So what we did is we created a daily snapshot, which contained all the changes from the previous day, deduplicated with the snapshot of the previous day as well, and created a new snapshot. And so if you want to know the current state of this whole sales order stuff, you just take the snapshot, apply the delta or the changes, and then you have the current state. And the snapshot is read optimized, so even people with which are only interested in batch inserting, they could just read the snapshot. It has, I don't know, 250 megabytes chunk, so it's perfectly readable, even with EMR or other technologies or Presto. And the changes table just reflects the changes of the current day.
Is this classical Lambda?
Yes and no, yeah. Yeah, it's. I think the difference is that in Lambda, you don't do it with one job. Usually you have two jobs, not combine it, but I don't want to judge this. Take it as Lambda architecture, if you want to. So the downstream consumers could distinguish whether they're interested in the changes only by just reading this changes table, which is a delta table, which is nice, which could be used for streaming as well. Or if they want to use the snapshot only, they can just read the whole snapshot once a day, and we're fine. Of course, to create the snapshot, we needed another job, the snapshot job, whatever, the snapshotter, which takes the snapshot of the previous day, applies all the changes, and creates the snapshot of the new day. And the cool thing is that we had snapshots for all days, and we have a whole changes table, so we can go back in time independently, which is nice. So we can even restore, or we could restore any point in time with both of these tables. But as the snapshot is pretty big and you need to join it to do all the processing, it worked better, but it was still a little bit slow. So usually over time, when the changes during the day get bigger and bigger, this was not succeeding. So what we ended up with is we load every snapshot into the cluster on just the hard disk. So whenever there is a new snapshot available, we just load it into the Spark cluster, and this speeded up the micro batch time by, I don't know, 4x or whatever. So bring the snapshot to the computation really helped here, but you need more disk space on the cluster. So this was the downside, but yeah, it worked actually. So this is where we are today. But I want to give you an outlook to show what our thinking about this solution currently is. So what's coming next? So the first thing is that we see is currently our product is only really able to be processed by Spark, especially the changes that we produce. The low latency product of, or the low latency part of our product is only currently processable with Spark streaming, because only there you have this delta read stream feature. And therefore, we will in future send the data to Nakadi as well, so that all the other applications, back-end systems and so on, can use these changes directly from Kafka as they consume other events as well. And we have a whole chain of tooling behind it to the data sent to the data lake again, and you have, I don't know, Presto table automatically created on this. So we would benefit from all this tooling behind it. Second thing that we want to do is we don't find the snapshot thing really well. If we would have the Kafka queue, we would have all the changes in the data lake anyway, because we have this archiver here from Kafka to S3. So we could rethink all the state stores thing, because if we are looking for the needle in the haystack and want to update the needle in the haystack, Parquet format, and Delta is backed by Parquet as well, maybe is not the optimal version. And so what we want to do is replace all this with the state store technology, which is more database based. So we are thinking about HBase or DynamoDB. The problem here is that during the day, during the streaming, this is not a big problem, right? So you have maybe 4,000 events per second at peak or whatever, which is usually handleable by most of these technologies or even Redis. The problem is the bootstrap. So imagine DynamoDB. So if you want to insert 500 million rows into DynamoDB, this is really expensive and takes time. So we are looking for a technology. We are not there yet. So you can give us advice how to do it. So HBase could be an option, because you could write the H files with Spark directly and put an EMR cluster on top of it. But yeah, let's see. So we don't have the answer for this. And if we would do it, of course, we would put the snapshotter on top of the changes coming out from Kafka and would create the same changes and snapshots based on the Kafka's topic. Okay. Next, so what did we learn as well? Oh, come on. SQL versus Scala. So I know this is a hot topic here, and I don't want to say that this is the truth for everyone, but at least we learned something with the background that we have that I want to share. So of course we started with the first integrations we did with Spark SQL. It was really nice. People knew SQL, and it was, let's say, until 100 lines is what was easy to read. 200 lines is, I think, the max that makes it nice to read. But adding more, we grew fast to 400 lines of SQL code. So I think this is a common pattern. You see this in data warehousing quite frequently. And what we also saw is that we violated the dry principle. Yeah, we repeated all the column names on and on, or we had certain case when patterns multiple times. And so this is not don't repeat yourself. Yeah? So if you see this and make a pattern analysis, you saw multiple patterns that are hard to replace in SQL. Of course, there are UDFs but even the joins with always the same columns, you cannot really abstract here. So, and on the same time, so how do you test maybe one line in the SQL? You cannot easily test it. So what you do is you execute the whole Spark environment for only one line. This takes some time, and then you get the result, whether it's good or bad. But if you use Scala, you could just easily have one method, and you have a unit test which runs in milliseconds instead of seconds, because for the 400 lines of SQL, the unit test you will not get under 5 seconds or whatever. So you cannot have a lot of tests for this without extending the build time much. And on the other hand, what we saw, especially in the beginning of the project, you need to refactor a lot, because you don't have the the final answer on how to structure the code and everything. So you want to refactor. And if you have parts of your code in Scala and parts in SQL, you cannot refactor. Yeah? You want to rename a field. Yeah, in Scala, it will be renamed by your IDE. But the SQL code still contains the old column name. So this is tricky, and even in, we haven't found a good SQL editor here, but it's really hard to refactor things in SQL. It's not as automated as in Java-based or JVM-based languages. So, and what we also saw is that, especially if you have all these events which provide nested structures, SQL is not really made for nested structures. So maybe I'm wrong. So there is support. You can even iterate over arrays and all this and create maps. But it's ugly. You repeat a lot of code if you are iterating over nested structures, or if you have 2 arrays and 2 events and you want to join them, it's tricky. Or you could expose the whole thing, but explode the whole thing, but that's also not nice. It's not really made for nested structures. So what we definitely end up is, okay, we want to go with Scala, and we've refactored many lines of SQL code by using Scala. So maybe it's slower, yeah? So I agree that the serialization, deserialization takes some time, but for the quality and the maintainability of the code, this was really a big gain by using Scala instead of SQL. Okay. Lessons learned so far. What we thought is, okay, we are replacing a data warehousing system or a data warehousing ETL with new technology. And we thought, okay, it will be similar. We will have these nightly jobs, but streaming needs a complete different thinking. So whenever you need it, it's good, yeah, and it's really valuable. But be aware that you need completely different thinking of how to do things. Also for deployment, how to monitor the thing, and all this. It's completely different. What we also learned is data warehousing doing with streaming is like back-end programming. So you cannot just put your BI engineers and say that build the data warehouse in PL SQL or whatever and put them on a project with Spark streaming. So they probably will fail. So bring some people in that have back-end programming skills if you want to succeed here, or they are used to streaming. So, but the cool thing is that data warehousing is not something else than backend programming anymore. So usually in the company you have, I don't know, 80 backend programmers and 10 people doing data warehousing anymore. But now you can integrate them and you only have backend programmers anymore because, or backend light programmers, data engineers doing data warehousing as well. Yeah, like I showed you in the previous slide, don't start with SQL because it's easy. So of course, yeah, the first 2 lines, everybody knows SQL. It's the first 20 lines of SQL are written really fast, but in our case, it was not maintainable on the long run, and how to refactor and also how to develop with SQL in this thing. Databricks Delta, so even if we failed with the merge command, what we see is that Databricks Delta succeeds Parquet in many things. So this metadata scalability, that you don't need to list all the files on S3 anymore, is really valuable. And if you do it right, you could even read the Delta table with the Parquet reader. There are some exceptions that you need to be aware of, but usually it works. So I can really recommend Databricks Delta here for this. And as it's now open sourced, you can even unit test. For us, this was a big deal to have Databricks Delta open source, because before this we used In production, we use Delta, and on our local unit test, we use Spark. So we had all the time this, if on production, then data format is Delta, and locally use Spark. And with this open sourcing of Databricks Delta, we could just use Delta for local unit testing, which was nice. What another learning is, especially if you have a bigger company and where you want to distribute the data, is make sure that the data is on S3. Okay, we are on AWS or whatever your persistent store is that is easy to read by many technologies. Currently for us, S3 is the technologies that almost every storage system can read. So therefore for us it was clear that we want to read the data from S3 and put it on S3 finally even after Kafka, so that even Redshift or other technology, EMR, can read it and you can easily distribute the data. Okay, that's it. Thanks a lot. Any questions?
Yeah, thanks for the talk. Interesting. The snapshot. Like one of the properties of the Lambda architecture is that source of truth is in the master data record in the batch layer, and that fault tolerance is recovered daily, let's say. With the snapshot, you propagate the updates from the stream to the next day and to the next day. So first question would be, how does it do fault tolerance, the snapshot approach? And second question, following on that, with your ideas of a state store, how would you see that being fault tolerant? Are you then overwriting the whole state from the history, from the history layer? And are you then updating through the day from the stream, and then next day again dumping the state? Or are you propagating state to the future from the stream? Thank you.
Okay, so maybe I answer the second question first. So if we need to rebootstrap the whole state store, what we do is we make kind of a green-blue deployment. So we prepare a new snapshot or delta table and pump everything there and reprocess all the events since our starting points of reading events. So we have a kind of a ready to be used second state store, then we interrupt the streaming job and restart it on the new state store. So I think that's why it's not called, to answer your first question, I think that's why it's not a classical Lambda architecture, because here our source of truth is the delta table or the just changes table and not the batch table. The batch table is just a snapshot to optimize reading of the changes and the previous snapshot. And so actually because we only get events, we cannot have all the current state of the system as a snapshot just from Kafka. Yeah, so we are not sucking the data out of a database. Yeah, where you have consistent snapshots, kind of. So if you only have events, then the events are the source of truth. So that's why.
So fault tolerance is.
Yeah. So what do you mean? What kind of faults do you think of?
Are you doing proper event sourcing? That the stream is the source of truth, like you say, and then. How do you deal with faults happening in that stream process?
That's why I'm asking for the fault. So we are fault tolerant. So for example, if there are late coming events, we are idempotent. So we can just reprocess them. And if there is a newer event for the same object, then it's just ignored. So we can reprocess everything easily. And with this SQS queue, which recognizes new files, it could even happen that a file in a yesterday's partition is written. We would just get an update on this, and Spark or the Databricks S3 SQS connector handles this for us.
All right, thank you.
Yep.
Hi.
Hi.
One of the points you mentioned, we are moving from SQL to Scala. So I got comments for my architecture also same thing. But my question is now the world is moving to use Spark SQL, nothing but it's under the hood they use catalyst optimizer, all the optimizers. So how do we use this, all the features when you go for Scala, all the things? This is my questions. Second question is not only this one, all the features, because it's open source world, right? So every month new features come, they may added under the hood. So to improve the performance with respect to Spark, SQL, all the things, because we are moving from data frame, RD, data frame, dataset, all the things. So second question is now, especially for Databricks or Spark 3.0, it's moving for miscellaneous AI, all the things. So in this case, how do we use this if we go for, instead of using Spark SQL, we go for Scala? Again, the way you mentioned like maintainability, all the things. So if you go for Scala also, the same issue will come, right? So this is the second question.
Okay, so I forgot your first question, but you can repeat it, sorry. So the second question, actually, you're right. So you lose some benefits from the underlying SQL optimizer on Spark. This is true, and I haven't do performance testing on this, but it's not that much slower if you deserialize it to Scala object and do everything in Scala. What I can recommend, and that's what we do, is we do some like type changes, whatever we do in not SQL, but with the data frame API. So we try to do as much as possible in the data frame API, and if then the data frame is ready, then we serialize it to Scala and not try to, I don't know, convert big decimal to long in Scala. We try to push it on the Spark side so that we can benefit from these optimizations. But actually all the joins and so on, I don't think that this is much slower. So, and basically in event integration, you do a lot of joins and then just map things. And so we thought it does not make sense to find an abstraction for this and just use Scala, because we can easily refactor this in our IDE and use unit testing for small pieces. Yeah. And what was your first question? Sorry.
My first question is, since we move from Spark SQL to Scala,
Yeah.
under the hood they are improving optimization, partitioning,
Yeah.
dynamic partition, everything is coming now.
Yeah. So
Now when you move this from Spark SQL to Scala, so these features we will not get when you implement. It could be data warehousing or it could be AI related miscellaneous or whatever.
yeah.
So we need to write the code to match. We may not write the code, may take time. So
Yeah.
now that we go to customers, they expect immediate. You want solution. It's not like you take one year. You don't develop from scratch. So
Yeah.
nobody customer will accept. They'll say, "Throw, you go out."
So this is what I mean. So of course it's faster to just start with SQL, and it's fast, but actually the customer should be also be interested in having a maintainable product. And I see a lot of Spark SQL code which just grows and grows and grows, and there's one little feature which, I don't know, almost doubles the SQL code because it's too complex to abstract it in SQL. So what should I say? Convince your boss to use Scala and give your best.
Okay, thank you, Sebastian, for the great talk, and thank you everyone for coming. You can still chat offline. Thank you.